Yeah, let's learn more about modifier. For example, modifier ammonium nitrate is used in the analysis of manganese in seawater. Okay, uh, so most interference comes from sodium chloride. Okay, so somehow you have to remove sodium chloride interference. Okay, in the case you can um, use ammonium nitrate. Okay, this ammonium nitrate reacts with sodium chloride, and the products are ammonium chloride and sodium nitrate. They are more volatile than ammonium nitrate and sodium chloride. So these compounds don't make smoke but cleanly evaporated. Okay, look at this figure here, and this the figure A is the temperature. Okay, as a function of time. So as you increase the temperature of the um, flame or furnace, then here up to, let's see, about several hundred degrees C, the sample is not atomized. It remains in dry state, and then when you increase temperature more, up to maybe 500 degrees C, char is formed, and then when you increase further more, and then atomize begins to start. Okay, yeah, like that. And this one, this figure P is the absorbance with respect to time. Okay, in this case, uh, the your sample is 10 microliter of 0.5 molar sodium chloride. Okay, and in this region, there is the temperature is between several hundred to about 500, and you see this signal. Okay, but here absorbance. You measure absorbance at manganese absorption wavelengths. Okay, but still at this region where the temperature is below 500 degrees C, you see a lot of signals. That's called smoking effect, uh, which is definitely what you don't need. Okay, you have to remove this part. Okay, and after atomization, okay, you see your sample peak from manganese. Okay, here, right? But when you add um, this one, uh, of course, sodium chloride and also ammonium nitrate. Okay, and then this reaction takes place inside the furnace. All right, and then they are all volatile. So this smoking effect now in this case is mostly removed. Okay, another modifier, magnesium nitrate, and it raises temperature for atomization of aluminum analyte. Okay, at high temperature, magnesium nitrate decomposes to magnesium oxide. Okay, uh, here, although on the no, in the absence of oxygen, but since it has oxygen, atom here, so at the elevated temperature, the magnesium oxide is formed, and aluminum in analyte becomes also oxidized to aluminum oxide. Okay, and then it decomposes to aluminum and oxygen atom. Okay, as long as magnesium oxide is present, evaporation of aluminum gets slower. Okay, by this reaction. Okay, 3 magnesium oxide reacts with solid state of 2 aluminum atom and becomes 3 magnesium atom in gaseous state and aluminum oxide in solid state. And first, so magnesium oxide evaporates. Okay, and without this magnesium oxide, no more aluminum oxide forms. Okay, and then this aluminum oxide uh, is decomposed to aluminum, and then this aluminum is evaporated. Okay, and now let's consider inductively coupled plasma. Mm. This is a very sensitive technique. Yeah? Although this instrument is very expensive. Okay, why this is so sensitive and so stable? Because the temperature is very high. Look at that. Uh, this is the temperature profile of typical ICP. Yeah? And the temperature is hotter than conventional flame by 2 times. Okay? So here, 4,000 Kelvin could be achieved. Okay, usually higher than 6,000 Kelvin. Okay, this temperature is really high. Okay, now sample is introduced from here. Okay, from the bottom. Since this part is very high, very hot. Okay, so complete atomization is possible. Okay, high temperature, stability, chemical inert argon in plasma eliminate much of interference encountered in flame. Since temperature is so high, such a the interference effect is easily removed. Okay, and so the system is better stability. Okay, and with this instrument ICP, simultaneous multi-element analysis possible. It is routinely done. Okay, ICP AES. Okay, here uh, at this extremely hot flame, and then all the elements are atomized, and then its emission from those atoms is detected. Okay, so this ICP AES is much better than flame atomic absorption, right? But how do we achieve such a high temperature? That is done by the uh, induced inductively coupled plasma here. You see this is coil surround this ICP. Um, this is the ICP. Let me see burner, right? And here you use argon gas to make argon plasma. Okay, and you need radio frequency. You see, to increase the temperature. Okay? Anyway, you see, the temperature maintains at very high temperature. Okay? This now is 2 turns yeah, around uh, this one, and the induction coil. This is induction coil, 41 megahertz. So this is they are made of quartz because this quartz can stand this high temperature. Okay, high purity argon gas is fed through the plasma gas inlet after spark from a Tesla coil ionizes argon. Free electrons are accelerated by the radio frequency field. Electrons collide with atoms and transfer energy to the entire gas, maintaining a temperature uh, to 6,000 Kelvin, maybe up to 10,000 Kelvin. Okay, the concentration of analyte needed for adequate signal is reduced by an order of magnitude with an ultrasonic nebulizer. Okay, you need nebulizer, yeah, to make your sample into a very fine the particle. Okay, uh, in nebulizer there is a piezoelectric crystal whose vibration frequency is 1 megahertz. Okay, with this vibrating uh, crystal, uh, the very fine aerosol is possible, and then it is sent to the plasma. Okay, yeah, this is the structure of ICP burner head. Okay, here is a two-ton induction coil, this capillary, and this plasma tube and coolant. Because temperature is so high, you need coolant. And this is a sample tube. Sample aerosol is introduced through this the tube. Okay, and argon gas is introduced to this tube. Okay, so argon plasma is formed. Okay, okay, and this is ultrasonic nebulizer. Okay, and sample is introduced from here, and this is piezo electric crystal. Okay, it vibrates at about 1 megahertz. Okay, now sample droplets what is broken into aerosol. Okay, and then uh, here along this heated tube line, and then it is eventually introduced to the plasma. Okay, and here is the the picture. And this table, look at that table. Compares the detection limits for nickel ion at 231 nanometers. Okay, depending on techniques. ICP atomic emission. Okay, detection limit is 3 to 50 nanogram per milliliter. Okay, and ICP atomic emission with ultrasonic nebulizer. Okay, detection limit, you know, even goes down to 0.324 nanogram per milliliters. Yeah, with the pneumatic nebulizer. Okay, this is ordinary nebulizer. You have a very good detection limit, but worse than when you use the ultrasonic nebulizer here. And graphite furnace and atomic absorption. Okay, the detection limit, yeah, is very much better actually. Okay, 0.02 to 0.06. Okay, this graphite furnace method is okay, but the best the detection limit could be achieved with ICP mass spectrometry. Yeah? I'll explain at the end of this chapter. Okay.